All right, hi everybody. Today we're going to be covering how to solve some of these addition of velocities problems. Real quick, I'm gonna try and clean this up just like a little bit. But what I want you to see is that as we go through, we're going to be doing certain things when it comes to adding velocities. We want to make sure we understand what the questions are actually asking us. And so for this first one, it says to calculate a displacement given a speed and a time. And so displacement, remember, just means how far did he go in the x direction? It's a little bit intense. And what we mean by that then is to calculate how far he traveled in that 169 minutes. So in order to calculate this, we're going to do a couple of things. First is realize that velocity is equal to distance over time. In our particular case, we were given a velocity in meters per second. We're also given a time as 169 minutes, but I know I want that in seconds. So the first thing I'm going to do is I'm going to convert that to seconds, and I get 10,140 seconds. If we're thinking about this guy's motion, he's going 45 degrees south of east, which means he starts somewhere at the origin, and then he travels 45 degrees below what we would consider east. And what we're trying to figure out is how far he ends up going. Okay, so then I'm going to do my velocity times time, and that'll get me x. And that'll be 3.53 meters per second times 10,140 seconds. It's going to be a big number. Gets me 35,794.2 meters, which is also 35, almost 36 kilometers. Okay, and that was the answer to number 1. Okay, next thing I'm going to do is I'm going to try to figure out some information about how he encountered a headwind averaging 2 meters per second, almost in the opposite direction to his motion relative to the Earth. So what was his average velocity relative to the air? Okay, so now what we're saying is that he was flying this way at this particular speed, and that he incurred a wind that went opposite of him at 2 meters per second. When it comes down to it, since these are directly opposite, all we have to do is subtract. So we're going to do v travel minus v wind, and that'll get his v average air, which is what we were asked to find. And for us, that means we're going to do 3.53 minus 2.00 meters per second. That'll get us 1.53 meters per second, which is his relative average velocity when it comes to the air. The last one says, what is his total displacement? So if this is the average velocity he actually travels at, then we want to know in 169 minutes at the average speed, which takes into account the wind that we're told about, we want to know how far did he actually go. So we're going to use our average speed that we just calculated to determine this. So we're going to do our 10,140 seconds times our average speed, which we calculated to be 1.53 meters per second. And we're going to get a smaller displacement. Does that make sense? Yes, because he's traveling in the opposite direction of the wind, and the wind is slowing him down. So that's exactly what wind will do in all of these situations, is that they're just going the opposite direction of the thing that he was actually trying to go to. Now, is it always going to be that they're going exactly opposite? No. There may be different situations that we will deal with. All right, problem 2. It says a seagull flies 9 meters per second into the wind, which means there is some kind of wind happening here. It says it takes the bird 20 minutes to travel 6 kilometers relative to the Earth. What's the velocity of the wind? So we know that the average velocity of the bird is going to be the bird minus the wind. Okay, that's something that we should be able to agree on because the wind is going exactly opposite. Okay, and we know that the V average can be found by taking total distance or displacement over total time. And this is something we talked about early on. We also used this symbol to describe it. So we can calculate this V average. We were given this. We want to find this. Okay, so we're going to calculate the average velocity first. So I'm going to do the I'm going to do the 6 kilometers, which should be in meters, so 6,000 meters. And we're going to divide it by the 20 minutes, which should be in seconds. So we're actually going to divide the 6,000 meters by 1,200 seconds. And that's going to get us 5 meters per second is the average velocity. Okay, so then I'm going to use that V average, the V bird, and I'm going to try to calculate the V of the wind using that equation we talked about at the beginning. So that means 5 will equal 9 minus V of the wind. So V of the wind comes out to be 4 meters per second. And we should note that it's 4 meters per second in the opposite direction of the bird. We don't have enough information to say exactly what direction. We just know it's the opposite of the direction that the bird is flying because we weren't told that we weren't told it was flying straight east. We weren't told it was dropping. We weren't doing any of that. Okay. All right. The next one says, if the bird turns around and flies with the wind, how long will he take to return 6 kilometers? So now we're saying, let's flip the bird's velocities, sign, basically. So now instead of 9 meters per second, he's going to fly at -9 meters per second. And the wind is still going to be 4 meters per second. So that would give us an average speed. This time instead, the velocities would be added, of -13 meters per second. We flip the sign on one of them. Now, saying negative and positive doesn't really matter here, so I'm actually just going to make this positive. I'm just going to say 13 meters per second, again, because in this particular problem, we don't have a direction. We don't have east or north or south to work with. So that's kind of something. The next thing I'm going to do is I'm going to try and calculate how far he would go in 6 kilometers. How long would it take him to go 6 kilometers at this 13 meters per second? So remembering that when we go to cancel things out, one of the things we want is everything in the same units. I'm going to convert that to meters. Then I want to get rid of meters by multiplying by the inverse of the velocity. It's like saying that 13 meters per second can be flipped just because it has those that fraction of a unit. So in order to figure out how far or how long it would take, all I have to do is divide the 6,000 by 13 meters, and I get 461.54 seconds. In other words, his forward trip takes 1,200 seconds. His reverse trip, when he flies with the wind, takes less than half the time. In fact, that is approximately 7.5-ish minutes. Okay? And then our last thing says how does the wind affect the total round trip time compared to what it would be with no wind? In other words, if there was no wind, and he was flying at 9 meters per second, and he wanted to go 6 kilometers, it would take him We're going to do the same calculation we did up here. Oops, meters on the bottom, seconds on the top. It would take him approximately this many minutes. Okay. If he did that times 2, that would be this long. And this is with no wind. In other words, if this is the only one where he goes back and forth, right? So this is with no wind. Now with wind, we said 461.54 seconds. We're going to add the 2 results we got before. So we're going to take our 461 seconds and we're going to add it to our first round trip time, or my first their time, which is 1200. And we're going to get about 27.7 minutes. And this is with the wind. So in other words, it takes longer when he has to fly against the wind, obviously, but the whole round trip does take actually a lot longer than he originally planned it would, I guess. And that's what we're trying to figure out. All right, next one is going to be a ship that set sails from the Netherlands, heading due north. So I'm always going to draw my vectors. And when I do, he's heading due north 7 meters per second. So this is going to be V of the ship. Okay, due north means 90-degree angle. The local current is 1.5 meters per second in a direction of 40 degrees north of east. So our river, or our ocean, is going this direction at 40 degrees. We're going to say V of the ocean. And it's got a speed of 1.5 meters per second. Our question is, what is V of the boat relative to the Earth? In other words, I want the resultant vector. Okay, now we're going to solve this just like any other type of addition of velocities problem. In order to do it, I want all of the Vx components. So for the ship, I can get X and Y. In this particular case, there is no Vx for the ship because it's going 90 degrees north, and the Y is going to be all of it. The V of the ocean, then, we'd have to solve for the components. Vy, oops, sorry, Vx we'll do first, and then Vy we'll do second. Remember that in order to calculate these, we do the cosine of the angle, and then 1.5 times the sine of 40 degrees. Just kind of little dream bubble to remind you of how to do component vectors. For the x component, I get 1.15 meters per second. For the y component, I get 0.964 meters per second. I'm going to double check that my mode is still correct. Yep. Okay, and then I'm going to do the total, which is going to be V Earth, if you will, remember? So Vx, I'm going to do the R's. Rx will equal 0 plus 1.15. Ry will be 0.96 plus 7, so 7.964 meters per second. These numbers do make sense, mostly because nothing is negative, etc., etc. R then and theta can be calculated using the formulas you've seen before. So remember the square root of Rx squared plus Ry squared, and theta R is inverse tangent of ry over rx. I'm going to pause real quick while I do this math. Okay, so those are my two answers. R is 8.05 meters per second. Again, that makes sense because the boat was moving at 7 meters per second and the current adds a little bit to it. And then the angle at which it's actually moving is slightly different than the 90 degrees it thinks it's moving. It's at that 81.78 degrees. So the effect of the ocean current is the same as the effect of the wind. It can minorly or even majorly, depending on how fast it is, impact the direction and magnitude at which something is moving. Okay, so that is the answer key for the 3 problems that you were assigned on Friday. I do just want to point out that the answers that I've just filmed are also in, if you look over here on the right, or on the left, sorry, of your screen, the content library practice problems. So if you go over to the left, you see content library and then practice problems. You can see any of the work that I've done, as well as you'll be able to access this video on YouTube anytime you like. All right, that's all. Once you're done with this, there are some homework problems that are posted on Office 365 for you to study and to work on today. Okay, otherwise, I hope you have a great day. I love and miss you all. Bye.